Well, good evening, everybody, and welcome to our November member meeting with Portland Urban Beekeepers. And my name is Cheryl Wright. I'm the nurse practitioner. I'm sorry, I'm not. I am the president of the Portland Urban Beekeepers and will be until our elections are finished. And our elections are happening right now. And I will be sending you an almost daily email to remind you to vote. We so far have had 20 people vote. Thank you very much for those of you who have voted. It will be a simple Google link you can click on and it will take you right where you need to go. You can vote only once, but if you change your mind, you are able to go back in and change your votes if something happens. Okay, so let's get started. So again, we always put forth why join the Portland Urban Beekeepers. As you know, our meetings are for free. We post the Zoom link for the meeting to come on our website. And then we post the meeting that we had last month on the website as well, which any public member is welcome to view. But by joining us, you can have access to our library, which includes books, candle molds, DVDs, and then the equipment rental, which is manual and motorized extractors, a refractometer, observation hive, a frame jig, and then we have our swarm list. So you do have to be a member to be on our swarm list. And then we also have our Bee Buddy connections, which I'll mention a little bit later in the presentation. And then we have free beekeeping opportunities at the club apiary, which allows you, if you want to figure out if bees are your thing, to get in there and get just suited up and play with the hive tools and do the frame inspections and see if this is really something you want to invest in before you make a big investment. So you can support our mission for only $25 a year. And we also have a Facebook page, which we do not charge. Obviously, it's just a social platform where anybody's free to ask questions and anybody's free to answer them. So you'll get a lot of different opinions. As you know, for every beekeeper, there's a different opinion on how something should be done. So again, as I mentioned, our elections, we will be running the elections from the 1st of November through the 30th. They will be closed on the 30th, and then final vote tally will be counted, and then we will make the announcement via email. And I mentioned that the Google form will be sent to each pub member. So if you get it again and again and again, and you've already voted, just delete it. But I just want to try to encourage participation. I mean, for instance, we have about 250 members, and if we get a 50% participation rate, we're doing well. So I'd like to see a little bit more participation in that. So our officers, so our candidate for president is Ian Horvath. Our vice president candidate is Jana Patterson. Our secretary treasurer will be Brian Fackler. The librarian, Katie Fackler, yes, his daughter. Our apiary manager, Bruce Kester. Our communications person is Jessica Anderson. And then our member at large will be Carl Strobel. And Carl will be new to the board, and he will bring a lot of experience and enthusiasm. So here's a little bit of a short bio on each of our members. Ian, he is a great guy, very warm and personable, and he's going to foster a collaborative environment. So bringing in both a new and experienced beekeeper, and you can read the rest about him. And then Jana is relatively new to beekeeping, but she's going to bring more of the board experience to the Portland Urban Beekeepers Board, as she's been an experienced board member. But she's also really into bees now, and so we welcome Jana to our beekeeping fold, and we're really enthusiastic about her jumping right on and volunteering to be a board member. So both Ian and Jana, you cannot go wrong. Our apiary is at Green Acres, which is in North Portland, and the exact address is 8940 North Bradford. And we suspended beekeeping for the year just because they're buttoned up and they're ready to overwinter. But we will resume probably in March, and we will let you know. Generally, we meet on the 1st and 3rd Sundays of the month. And the time is generally from 10 a.m. to noon. And you can stay a little bit later if you want. But if you do join a work party, remember to go to our website and click on the apiary link. You'll get a drop down, and there are electronic forms that we need to fill out that are releases. So our Bee Buddy program has been virtual now for about 6 months, and I just want to keep it in the forefront of your mind because it's for it's one thing to beekeep and sort of, you know, in the old days back before COVID, we would get together in a room, and it was a very social activity. And beekeeping is really a lot of fun with friends. And so this is a way that you can look on a map and you can find a mentor or you can find a friend who's in your neighborhood and maybe just do some beekeeping together. So it's very easy to access. You just go to our website and you log in. You do have to be a member for this. Click on the resource tab, and then there's a Bee Buddy map. And you click on the hot link, fill out your information, and then submit. It'll take a day or so. Ian has been running this great new build, and then he will get your information up there, and this is what it looks like. So you can see that the people who want mentoring or who are newer beekeepers are in purple and the mentors are in aqua. And when you click on them, this is what comes up, the name, and then contact information, exact address, and then a little bit about them and what they specialize in. So we are having more and more mentors signing up. I would encourage those of you who have a lot of experience to please be a mentor. And then our newer beekeepers, please sign up so that we can start networking and becoming stronger in our beekeeping. We did decide to cancel the honey tasting. This was a board decision, just based on the fact that meeting indoors in such a small area is not going to be, I think, a lot of fun. Some people will be masked, others won't. Nobody wants to check vaccination records at the door. And so we're just going to put that off until next year. But you can enjoy your own honey harvest if you did. After Bee School recordings are still available. So if you have any friends or anybody who's interested in being introduced to beekeeping, they're $45. You get access to all of the recordings. And we use Dewey Caron's book, which is Honeybee Biology and Beekeeping. And we follow along with that. And it's a great course and people seem to really be enjoying it. We will be offering New Bee School next year in 2022, right? So we'll look forward to seeing anybody at that point as well. So Steve Gomez is still looking for people to raise queens and learn more about raising queens and maybe even having a queen club. So if you're interested, you can contact him. Here's his email and his phone number. So get in touch. I think that would be a really fun project. And here we are in our favorite season of winter. So let's hope that our bees are buttoned up and ready to go. So in November and December, you can see that our brood is dramatically decreasing. Our adult population has been decreasing all along, but hopefully is fairly static at this point with our fat bees who are going to overwinter. And just remember that it's this December, it's the winter solstice, when we like to do our oxalic acid. We get our most effective treatment here because of the so little brood. And if we do that, if we're able to get these mites, and we've been treating for mites all along in the late summer and all through autumn, we do that one more treatment, then in the fall, what we would like to see is we'd like to see very, very low mite counts as our bee population starts to grow again. And then by starting with a very low mite population, hopefully we'll have a slower mite buildup so that by summer again, we can start intervening. And so this is.
I want to get together with Dewey, come up with a schedule.
We can hear you, Bruce. If you might want to mute yourself, that would be great. Thanks. Okay. So what should we be doing in our hives in November and December? So basically, this is the quiescent time for beekeeping. So we need to be organizing, cleaning, repairing equipment. If we're going to do inspections, they should be minimal and preferably no manipulation. So as you know, just popping the lid off, maybe making sure that maybe you can see a cluster if it's a nice day, but really less is more during the winter. So be planning your next bee year with your nukes, your splits. How are you going to keep swarms from happening? How are you going to manage mites? Are you going to rotate treatments? Are you going to do brood breaks? Make sure that your mouse guards and your entrance reducers are on, weatherized, and of course that's what tonight's meeting is all about. If you can have a rain guard, insulate, consider closing your screen bottom board. Varroa mite management, as I said, for during the winter solstice period between maybe Thanksgiving and Christmas, if you can get that oxalic acid treatment in. Evaluate your stores using the Heft method. If you don't have scales, just reach back there and see how heavy that hive is. Make sure that if the weight's low, you have a feeding plan, which will include dry feeds such as candy boards, fondants, dry sugar. And then grab a new bee book or subscribe to a bee journal, attend bee club meetings and/or Bee School 2022. So again, just checking brood patterns, just to remind you that as we go into the wintertime, that your brood pattern will be becoming more and more compact, and that's normal, and that's what we expect. Hopefully your overwintering bees will be fat and healthy and virus-free. In the spring, this is what you're going to see, a more of an expansive brood pattern. And if you pull up a brood pattern like this is pretty spotty, not very consolidated. So that suggests a failing queen or something else might be going on in your colony. This is an idea for a dry sugar supplement with cakes, and these guys have put in a little shim board and they've screened it so that they can keep the bees fairly controlled with their wax making and yet do a nice supplemental feed during the winter. And if you're good and you ask Santa Claus nicely, you might get a FLIR camera, and then you can go out in the freezing cold and take photos of your beehives and look and see where your bee clusters are. So orange is hot, and you can see also not only where your cluster is in the hive, but you can also see heat leakage. So maybe if these people had an entrance reducer on, they wouldn't be having all of this hot air running out the front. And it also stresses the importance of minimizing these upper entrances. These guys don't have upper entrances on it, but Santa brought my husband a FLIR camera, surprise, and I happened to borrow it and noticed that there was quite a bit of heat escaping out those upper entrances, so I took care of that. But this is a fun way to monitor your hives in the wintertime. Watch out for the mice, you know, they're cold too, so get those mouse guards on. They're so cute. And then also remember that if you get a dead out, you know, I mean, maybe something happens during the winter and you open your colony and you see something like this. It's ugly, but it's not a problem. Clean it up and you put some bees in there and they will also finish cleaning it up. So there's not much you can do about the wax moth. If you have frames and you know that that you're not going to be populating this at this time of year, you can freeze them. You can put them in plastic bags, and some people put even a little mothball in there, but that's, you know, another toxin you're adding to the wax. So that's up to you. But just be aware that while it looks ugly, it's not the end of the world. Your equipment is usually salvageable. Please remember in the springtime that we do have beneficial wasps who are also pollinators. These are not yellow jackets. Don't kill everything that's black and yellow with a stinger. We like and need all of the insects that we can have. Does anybody have any questions?
I didn't get a chance to finish writing down the email for the person who's doing the Queen Club.
I'm sorry. There you go. It's a kind of a weird email, so it's not like, you know, stevegomez@gmail.com, but there you go. For anybody else that might want his email and address. And he's really a great guy. He's fun. And the other thing that he does, if everybody wants to make a note of this, is if you have somebody complaining about a bumblebee nest, like the bumblebees around here, they love defunct birdhouses. The birdhouse falls out of the tree onto the ground. The bumblebees move in. They do their thing, and then in the springtime they get a little aggressive, and people just completely freak out. And you can call this guy Steve, and he does bumblebee rescue. So, and he'll come anytime, anywhere. He's not really geographically isolated. I don't know why he does it, and I don't know what he does with these bumblebees. I know he doesn't hurt them. He does rehome them in a safe environment. But I do try to let people know that bumblebees are the best pollinators for blueberries and tomatoes. So if you want a really good crop, you keep those bumblebees around. Anybody have any other questions or concerns? Okay, well, I'll introduce our speaker tonight is Bill Hesbach. He's a master beekeeper. He lives in Cheshire, Connecticut. He owns Wing Dance Apiary, and he produces a line of honey called Fat Bee Honey. And he's going to talk to us tonight about understanding hive thermodynamics and insulation. So Bill, welcome. And I'm going to stop my share, and I'm going to try to find you and make you a co-host.
He is under Connecticut Beekeepers Bureau.
Thank you.
Yeah, I'm
Dewey.
listed under Connecticut Beekeepers Association.
Oh, there I see you. Hi, welcome.
There I am. Hi, thank you so much.
Well, you're
let me get
welcome. Hold
my,
on. Hold on just a second while I do
Okay,
my,
yeah, my share screen is disabled, so you just have to put that on. In the meantime, I'll get my presentation up.
okay. Oh, let's see. Okay, you got it.
We're good now?
You're good to go,
All right, let me see if I can.
and you sound good.
All right, that's great. That's another good plus thing. Let me just exit my share screen and get on to sharing this. Okay. Okay, great. Okay, you should see my presentation,
I do. I see your pictures. They're beautiful.
but you won't see, now you should just see the one slide.
I do just see the one slide.
All right, so thank you so much for having me here tonight. It's an honor, actually, and a pleasure to be talking to folks so far away. I have talked to other folks on the West Coast and given them this talk, and hopefully you'll get something out of it. There's lots to think about in tonight's talk. I have a picture here. I was pleased to see that you get some snow in your. I mean, I don't want to be alone in that winter scene. This is just something I snapped in part of a
Yeah.
bee yard.
We don't get snow like that. If we get snow like that, we would completely freak out. We maybe get 2 or 3 inches on a bad winter. Mostly it's ice.
Okay, so you would freak out with this. Okay, so
We
that's,
would.
yeah, we don't, so we get this, but not as much as you might think. We are in a colder climate than you, obviously. And we're going to talk tonight about, let's just get some ground rules about questions. I don't have any problem with anybody asking a question whenever they want. I just ask that it's pertinent to whatever topic we're discussing. That's all.
Yeah.
And if folks put something in the chat, I'm imagining you're going to be the one that answers or asks questions out of chat. Is that-
Yeah, I'll moderate the chat box, and
Okay, great.
And then if you glance over and something catches your eye and you want to address it, that's fine. But generally, I'll moderate that, and people don't
Yeah.
generally tend to break in and ask questions during
Okay, all right.
during this
Yeah.
talk.
Okay, I don't have the chat box up, so you can take care of that.
Okay.
All right, so what you're seeing here is my colonies and the way I winter some of them. And that is what I refer to as a condensing colony. We'll talk a lot about that in a little bit, and you'll understand the principles under which I'm describing this particular way to winter bees. It's unusual in that it simulates. It's natural in that it simulates a tree colony, but it's unusual and outside normally the common understanding of how bees survive in winter. But I'll flesh that all out. I want to just let you know in the beginning that we know we can use our own infrared photography to see a lot about the way bees thermoregulate and how they manage the winter cluster. But the movement of the bees inside that cluster and those heater bees that participate in the cluster still is mystery to us, and how they change places and what they do. But let's start off with thermoregulation, and I'm going to use infrared photography to illustrate some of the points. So here you have a photograph, by the way, I just took a little bit. The ambient temperature was 62 degrees when I took this, and you can see in the infrared photograph on the right. And you saw one earlier also. You can see the bees are the warmest thing on this box. And in infrared photography, the warm areas are the hottest areas. And as you progress away from the warm areas, the colors get deeper and deeper until you see it at this point. This grass is the coolest thing around this particular little tiny top bar hive that I threw a swarm in early in the season. All right, so there's what it looks like in natural light. Of course, you don't see anything. Infrared light, you get this heat signature from it. IR is actual heat that's being emitted from those surfaces. And in this case, you can see the bee bodies are giving off lots of infrared radiation. They're giving off heat, just like your body gives off heat. All right, so if I take that top cover off and look down on that cluster, those top bars with an infrared camera, you can see exactly what was explained to you earlier. You can see exactly the position of the cluster. That's in this case, the warmest part of these top bars. It looks like it's around bar 6, 7, 8, and 9. I recently touched these top bars. You can do this with your hand also. You don't need a fancy infrared camera for top bar hives, but for other hives, it's much better to have an infrared camera. But for top bar hives, you can just feel the heat on the top bars and you'll know where a cluster is. It's actually moved a little bit over to the right side of this picture as they moved away from the feeder, which I was feeding them in. But there we go. Again, the principle is the cluster is the warmest part. There's a mantle of bees that the core of the cluster is the warmest part. There's a mantle of bees that surround that are a little bit warmer. And as you get away from the core, the temperatures get lower and lower. All right, and if you don't believe that in the IR version of it, you would not do this to your colonies in the winter, but if you did lift a box in the wintertime and you broke a cluster right in the middle, like Randy Oliver did in this photograph, and then you smoked them bees, those same bees, you notice that the bees in the mantle part are not likely to move away so fast because they can. They're in that area of temperature where their thorax is okay to keep them alive, but their abdomen and wing structure is below their flight ability temperature. And then they have to warm up a little bit to move off to the sides. So they stay in that mantle until they warm up. Right, so where is this heat coming from? So I'm going to talk a little bit about how bees generate heat. And you can see in these two IR photographs, the one on the left is illustrating what heater bees look like up close. And essentially, heater bees are using their indirect flight muscles in an isometric state for them to generate heat. It's the same kind of isometric exercise you might think about if you were doing a plank. I mean, that's a common sort of challenge that people try, the plank challenge, where you just stand with lay down with your toes and your arms outstretched, and you get the feeling of what it's like to hold an isometric pose. And bees can do that for about 10 minutes inside of a cell. And you can see on the picture on the right, that's a beautiful sort of illustration of what a cluster would look like if you were looking inside of it. This is probably from some kind of a colony where they lifted up the box and took an IR picture. I'm not really sure. But the temperature range is over here you might want to look at. These are very, very high temperatures, somewhere around 108 degrees and Fahrenheit. And that gets to the point where bees are having a hard time making a living. Above that, they are in a danger zone. So there's a couple of thoughts about heater bees. One is that, they're sacrificing basically their life as a heater bee in a colony because they are oxidizing their musculature and it short lives them. That's one theory. I've read another couple of papers that sort of challenge that and say that, well, heater bees don't really suffer that much from being heater bees and they're fine. And when I'm talking about heater bees, I want you to make a distinction between these bees and all the rest of these bees that are up to temperature. There's lots of bees here that are warm, and there's some that are very cool, the darker ones. And then in the center here, you're seeing some really heated bees. And basically, I'll go over this in a little bit of finer detail as we go on, but I'm talking about heater bees that specifically heat this core area of the cluster, and usually that's about 10% or less of the bees that are in that core structure. So I mentioned this, the thermology of wintering bees by Owens. He was a USDA scientist, and he did this extraordinary study over 5 years where he insulated some colonies, heated other ones, and then had some controls. And I mentioned this at this point just so that it's a very accessible piece of scientific work. If you get a chance to look that up and you want to read a little bit up, it's cold. You know your bees are in cluster, you know they're in hive, you want to see what they're doing under all of these different heat, natural ambient heat ranges. You can go to this study by Owens, and and as I said, it's open source, and you can learn all about it and see the marvelous sort of illustrations that they drew back in the day when they took 2 million data points to put together these. One of the slides I'm going to show you in a minute here. All right, so, whoa, what happened to that? Okay, what are you guys seeing? All right, so let's see. Okay, so I don't know what happened to this slide, but it's supposed to say that the bees are head down in cells, and I was doing a little bit of editing today. You're seeing the first version of this. I added a couple of slides to clarify things, and this one didn't get quite edited the way I wanted it to be. I'll show you on the next slide what this is all about. So bees generally are head down in cells when they heat, and you can see that from this single bee in the center of a cluster, in the center of brood. It's a very efficient way for bees to heat. This particular bee can raise its body temperature up to, as I say, 108 degrees Fahrenheit, and it can raise the temperature of this brood that's surrounding it to significant numbers so that they are alive and well. That's what heater bees do inside cells where there's brood. Where there's no brood, you would see it on this slide over here. Sometimes in the wintertime, at the end of the season, we find our bees in this situation where we see a bunch of I'm going to go back to out of this thing for a second and just edit this slide. Hold on. Okay, that's better. All right, so you generally find this, and there's this mythology about what's occurring on a comb like this, and you might hear this from folks in the room saying, well, hey, this is the bees were in their last desperate attempt to get the last bit of honey out of the cells, but that's not actually the case. This is the way bees form their winter cluster. They need empty cells to do that. And the interesting science behind the wax structures of this cellular matrix that bees are using to heat is that the sidewalls of a typical cell are only 70 micrometers. It's a very, very small, thin filament of wax. And in the terminology of thermology, it's called adiabatic, meaning that it makes no difference for the conduction of heat. So those bees are virtually side by side inside those cells. And if there's heater bees in there, they're literally from a thermographic standpoint, they're actually touching each other. So the wax makes no difference, no resistance at all. All right, so I'm gonna I'll point out this a few times, but I want you to notice that on a lot of these illustrations or slides, you'll see some science below it. Most of this science, almost all of it, I guess, is open source, so you can get it anytime you want. If you want to learn more about how heat flows and carries on to these different cells that have brood, that have pollen, that have all other interesting air, all of that science is done, and it's explainable in common terms in a lot of the science that I'm quoting. And this is the one that would explain more about that study down there by Marco would explain a lot more about what's going on from a thermodynamic standpoint in comb if you're inclined to want to go to that depth. All right, so when bees are head down in cells, I just want to show you this sort of these are called isotherms. They're different temperature gradients. And I wanted to show you the sort of superior dynamics of what one bee can actually do. One bee can actually heat with its head down in the cell, or will produce this heat signature up here. Not quite as warm as you might think, but somewhere around 37 C. And if somebody wants to put up most of this talk is in centigrade. So if somebody wants to put up a conversion chart in the chat, that would be good. And then you could read off the Fahrenheit temperatures if you're inclined to want to do that. Increase that heater bee population by 5 bees, and you get this incredible heat signature, very, very warm, up in the 40s, possibly, but in brood range and well within the necessary heat range to keep a core warm in the wintertime. All right, so heater bees, head down in cells, they make wonderful patterns of heat when they do that, and they can warm the core. We'll talk a lot more about how that occurs. All right, so bees, I think you may all know this, but bees use their indirect flight muscles in 2 ways, one for flight, and in that case, it's an asynchronous muscle fiber that just expands and contracts and vibrates the thorax of the bees, and the wings move on these sort of hinged areas. There's nothing directly connected to the wings. For the flight muscles, there are indirect flight muscles that are connected to the wings, but those are for other purposes, like the pitch of the wing and all of that. The angle of attack toward air and all of that is all dictated by the indirect flight muscles. But we are going to talk only about the direct flight muscles, but we only talk about the indirect flight muscles, which makes it possible for them to do isometric heating. In this case, they're balling a queen, but in the other IR photographs you saw, they were just generating heat. They're generating heat here too, but this is not an infrared photograph where you would see the heat that they're actually creating to ball their queen or save their queen. We don't really know what goes on in some of those queen balls, but if you want more information about this whole idea of how the fiber muscles work in bees, check out that study below. All right, so I talked about this. I'm just going to emphasize it. I wanted to show off some of my own dissection. This is what bees' vertical and horizontal flight muscles look like if you remove their head and take a look inside with a microscope, dissecting scope. And you can see these are the muscles that they put into this isometric state, as I mentioned before. It's like that plank exercise. And then this whole frozen thorax, which is locked down with this neurological signal that puts the flight muscles into this isometric state. That sort of motion is dampened by the scutellata, which is right on the back of the thorax of the bee and filled with hemolymph. And that plays an important role when the wings are actually being moved by the thorax, sort of a cushion or a shock absorber. But in the case of a heater bee, the scutellum plays a role where it sort of like aids the lockdown thorax at the same time. All right, so part of that thermology study that I talked about early, the conclusion is laid out the whole collection of all of that data over all of that 5-year period, came down to this one figure for an example of what kind of occurs, the average of all of those thermocouple readings. And it's something that we all know about brood. If a colony has brood, then the temperature in the middle of that brood nest is somewhere in the 90s, which is verified, by the way, over here with a colony that I took one of my insulation sleeves off and took an IR photograph of. And then as we get away from the core of the brood, we go out toward the outer reaches and toward the mantle, the temperature drops. And when we get out to the outer edge of the bees, we're down in the 40s and sometimes close to 50 degrees. This is the sort of borderline for Chilcoma. And the next, I think the next slide I'll show you, or the one after that will show you some of the limits of that cluster. Right, so the principle, the reason I'm showing you this is again to let you know that we're going to talk a little bit about what goes on right here, or we have been talking about what goes on here to maintain brood temperature. And the same sort of principles apply when there is no brood in the colony and bees are just heating that core. Now, in that instance, it's a different temperature profile, and I'll talk a little bit about that. Bees don't heat their core to 90 degrees if there's no brood. Right? The only time they do that is when there's brood, because of course they can't get brood much lower than those mid 90s, or it'll freeze out and you'll have chilled brood. It won't hatch or emerge. All right, so let's take a look at another sort of temps in the winter cluster piece. If you were to look at if you were just curious about where your queen might be during those winter months, she's most likely on that center frame, that center frame would probably be in the center, probably be the warmest part of the winter cluster. You can see her in this. I think you might be able to see her here. She's this largest bee. Her head's warm, but her abdomen is sort of like the color of the rest of the bees in that center cluster. You can notice also that there are some bees in here that are warmer than other ones, and those are the heater bees doing their job. And as we get toward the insulated mantle, we get a very different temperature profile, much cooler. All right, so let's take a look at some of the limits, and these are approximate numbers, of course, but they have decimal points after them, which wouldn't indicate that, but they really are. I mean, below 42 degrees or so, bees go into a chill coma, and they can die. And if they have to be in a chill coma for a while before they die. They can live fairly in a sort of torpor for 50 hours or so. I mean, I've experienced premature collection of what I thought was a dead hive and put it into one of my warmer spaces and found 1,000 bees flying in the garage or something the next morning because they were just in a chill coma and resumed their activities after I warmed them up. And then the inner core's average temperature is about 70 degrees. And then, as I mentioned, with brood around 95. And then we have some theories about how bees might move between the mantle and the core. And one of them that was common for a long time was that bees on the outer edge of the mantle are signaling somehow they get cold and they send some kind of mysterious signal to the inner core, and then the core begins to generate heat and warms all the bees up in the entire cluster. I think that's been challenged enough at this point. So the latest sort of theory about it is that it's possible that bees are migrating between the mantle and the core, likely based on their hydration needs, because bees in the core are warmer and the air is warmer, it can carry more moisture away, and they live sort of in a in a desert environment. So their metabolism is elevated a little bit. They're using the respiring moisture that's being carried away by convection. And then the bees on the outside mantle are cooler. They actually use more resources, but they're not capable of being able to rid themselves of the moisture they need to rid themselves of. So it's possible that one of the explanations that we've been talking about for a while now is that bees likely migrate from the center of the cluster to the outside mantle to gain moisture, and the bees on the outside mantle migrate slowly to the center of the core so they can dry out. And there's a great article by Mobison and ABJ back in '98, and he talked a little bit about that and it's an interesting discussion. He has nice illustrations and so on and so
Really
forth.
interesting about what the bees do in the winter.
Excuse me? Okay.
Sorry, I think somebody had their mic off or on.
Okay.
They
All right,
weren't
okay.
muted. Sorry for the interruption.
Okay, all right. No, I thought that was a question.
Yeah.
Okay, so, all right, and then the other sort of morphological interesting trait about bees is that on their thorax, they have bifurcated hair, and that hair traps heat, just like down on a bee's feathers. So, or down from a bee, from a bird, and and as the temperatures are lowered around the cluster, the ambient temperature gets cooler, the cluster tightens. You can see that from the, if you see that study that I mentioned earlier about the thermology of wintering bees, you'll see those actual photographs of the those pictorial diagrams of the isotherms where the bees are huddled together really tight when it gets cold. And when they do that, their thorax is touching, they end up being able to create an incredibly effective insulated shell, right? And they can do that by way of their bifurcated thorax hairs. And I know that's the case, that they have the hairs. I know that they cluster that way also. I've seen that, but I also know that their bifurcated hair exists because I had to shave it off, or I have to shave it off when I do dissections of musculature under the thorax. So I just thought that, oh, and then this is a question I get a lot about, is there any difference between the plastic comb and regular natural beeswax comb? And the answer is, from a thermal conductivity standpoint, when you look up the properties of both wax and HDPE, which is the plastic used in most plastic foundation, it's the same. But as I mentioned earlier, the wax is so thin in the cellular structures that it provides negligible heat resistance. So it's really just a support structure for heater bees or any bees that are in the cluster. From a thermal standpoint, it just doesn't exist. Bees might as well be just touching each other. And that explains why we can think about a cluster as a unit rather than thinking about bees clustered around individual combs and then having a bee way between them, or a bee seam, however you term that, and then another comb with bees around that inside. So if you think about it from a thermal standpoint, and that's the only important thing for a cluster, is that, as I mentioned, that word adiabatic, it means that there's no resistance to heat from the comb. So that's the wonderful part of their adaptation in life. All right, so this is the point where we're going to begin to talk a little bit about heat loss, and then we get into ventilation and all the rest of the talk. So is there anything that folks want to, I went over a lot of material. Is there anything that folks have a question about? before we move on?
So Jason asks, do bees need cool weather to winter over? What if I have them in a barn that keeps it above 40 to 45 degrees so that the bees don't, I don't know what HAC means, but.
I don't know, but yeah, they'll do fine in there as long as you got to keep them at an exact temperature. And if I was going to do that, I would do some research of what the Canadians do with their indoor wintering facilities. They keep it, they overwinter thousands of hives inside of buildings. They have to control the humidity at that point, but the temperature's right in that area. And in that area, that's the most efficient use of fuel for bees. And you can keep them in those, you have to have it regulated. It'd have to be perfect, or the bees would be, if it gets up to 55 or 60 degrees inside there, they're likely to fly out of that box, and then that might be a disaster because they'd go to the windows and not get back in. But, so yes, but do some research on what temperature and how you do that, how you keep it at that temperature.
And then, so one other person asked, he didn't understand about the foundation. Does it lessen the heat transfer? So
It's
he's
in-
talking, or
Yeah, the
unlike wax?
foundation, yeah, the foundation is, well, the wax cells, I think is what we're talking about, right?
I think so.
Yeah.
The
wax-
plasticell versus the wax cells.
Yeah, there's no difference between the way that they're invisible to the resistance of heat. They don't resist any heat. They allow it all to flow through. So from a thermal standpoint, all they are is a structure to hold the bees. And all the heat that's conducted by the heater bees that are in those cells moves around in that structure freely and is not resisted by it. Thanks for that question.
Question on the heater bees. Do the heater bees have to, or do they always perform the heating activity within the cell? Or if
No.
they're in the cluster, they'll just perform that as well?
No, well, heater bees usually are head down in the cluster because it's the most efficient way to conduct heat between other bees around it. Right, but they're down in that, as I said, there's no resistance from the wax. So a bee inside of a cell has about 2.6 or 3 or 4 bees that surround it and heating all of those and also giving off heat to the rest of the cluster. So it's the most efficient way for bees to heat a cluster. Now, of course, when there's brood, a heater bee, there's bees, because bees generate heat all year round. They have the bottom of their thorax in contact with the top of a cap of a cell. So there's no air between them. They hug down on top of that cell and heat it from there. So heater bees function in both cells and around on the comb. But I want you to look.
Well,
Go ahead.
one more question, please. Can
Sure.
any worker be a heater bee, or is this a specialized job?
Well, we don't know the answer to that question. I'm so sorry. I've done so much research trying to figure that out. And there's no science that supports it. All the papers and all the thermography and everything that has been done just shows bees heated up, like this photograph I'm showing you here. This is a heater bee, and that you might consider a heater bee. These bees are all warm around it, sort of just, and we know from observation that bees leave the cell after a period of time. So a heater bee won't stay in a cell forever. And the period of time seems to be around 10 minutes. And whether or not, my private thoughts on them, and of course, this is not science, it's just my thoughts on from what I've read, is that it must be a bee that is equipped with enough honey and energy to become a heater bee. So somehow, it knows it can be a heater bee, and it uses and it just gets into that cell. We can see bees go in and out of cells, but we don't know if it's a special polyethylene. Does polyethylene play a role in this? Is bees at a certain age are heater bees and not other ones? So
How do the bees get feed? Do they rotate in and out of the cell?
well, no, they have access to stores. All right, so when they break cluster, they have access to stores, and that's how they get energy, right? They're consuming honey. That's why we store them with a lot of honey. Yeah, that has to happen. They have to have resources to live. If their honey runs out, they die, right? Or if you don't put any emergency food on them, they die. Yeah, they have to have this. The whole assumption and it's a very good question. Thank you so much for asking it. The whole assumption here is that they have access to stores on occasion when they break cluster or they're right next to stores, and do other bees that have better access to store bring those stores to the center of cluster, the core? I don't know. That's another one that I wish I knew the answer to. Anything else? We good to go?
We're good to go.
All right. All right, so we're going to talk about the ways that bees lose heat, and we're switching to now this whole idea of how clusters survive and what's required for them to survive, and then how this ends with how we can, I think, accommodate their sort of inherent biological needs by providing them with a wonderful envelope that allows them to function naturally. So let's go through the steps here. So conductive heat loss through contact. So a heater bee goes down into his cell, it loses its heat, right? That's conductive heat loss. The conductive heat loss plays a role also in bees that are tightly together in a cluster. They're touching each other, and there's heat that's conducted between them. You can consider it loss because it's energy that's being used for that purpose, right? So to heat them, to heat the core. The next is convective heat loss, and that's the one that we're going to talk most about. And that's the one that occurs around the cluster, and especially on the surface of the cluster. And also, that also is regulated by the bees in precise increments. As they expand and contract the cluster, they allow more convective currents to go through it. And that's how and those are minute adjustments. And I just want to warn you ahead of time that I'm going to emphasize that again when I discuss added ventilation, because what bees are capable of being able to do when they make these precise little adjustments in the way that they move their the tightness of their cluster in and out, they can't do if there's a constant stream of cold air that goes through the cluster. All right, so that's you can consider convective heat loss as a wind chill factor. And then the last one is what we've based a lot of these photographs on, which is IR, or radiant heat loss from their bodies. Now, that's not something that we think a whole lot about, but any warm body on the planet, including you and I, all lose heat that radiates off of our body. If you can take a picture of your face and you have a nice jacket on, but your face is exposed to the outside, if you took an IR picture of yours, your head would be hot, just like that. Maybe not as hot as that heater bee, hopefully, but you would see your own radiant heat loss. All right, so the question, of course, is there a way to capture some of that radiant heat loss and focus it right back on the bees? Now, I have to tell you that one of my former lives is in engineering. As an engineer, I was responsible for the orchestrating the efficiency of building envelopes. And one thing that we considered when we built structures that were conserving heat was the radiant heat barrier. So we use that to reflect radiant heat back onto objects we wanted to remain warm. It's the same thing as the same principles you would use with one of those space blankets that rescue folks work. It's a thin mylar, shiny sheet that you can put over a person. And what that actually does is does a few things. Keep some convection currents off of them, but it also will radiate back to them their own IR loss, right? So it keeps their bodies warm. And can we do something about that? I'm going to show you a way I think you can do a little bit about it, not that much. I'm not going to suggest that it's a savior for bees, but it does have we can do something with that. All right, now cluster size matters. With heat loss, I'm going to do a little bit of math with you right now, but you're not going to do the math. I'm just going to explain it to you. And the cluster size matters because there's a relationship between the volume of the core and the surface area, or the mass of the core and the surface area. You know, the core of we've been talking about the core all night, and the core is where the heat is generated, and also where the heat is conserved. And if there's a relationship between the mass of that core and its surface area, let me show you. If you will accept the premise that most of the convection loss is on the surface area of the cluster, then this formula will make some sense to you. So if you look at basically a 10-inch cluster, you measured that using the formula in that little basketball on the right. I did the math for you. The core mass of a 10-inch cluster is like 523 inches, we'll say. The surface area of that 10-inch cluster is 314. So in that case, a 10-inch cluster, its mass is 40% larger than its surface area. What does that mean? That means that its ability to be able to conserve heat is 40% larger than its loss on its surface. All right, so a 10-inch cluster can hold more heat. If you decrease that cluster size by 5 inches, the formula reverses, and the core's mass then is 21% smaller than its surface area. And that's why you see these minimum B seams that can survive winter. I mean, the thermology studies that do the math models say that that's around 7,000 bees or so. You know, if you have a colony that's going to go into winter with less than 7,000 bees, and some of the science I read on it brings that bee cluster down to 4,000 bees, which would be conservative. Those are the limits where the surface area is just consumes too much of the convective loss, and the core is not capable of being able to keep up the heat. Right, so there's a relationship between the two. Now, you can see it here, which in nature, and you just know that that little cat on the right, is protecting its core, makes its core denser and its surface area smaller. If you look at the cat on the left, you can tell that cat would, of course, cool faster because it's exposed surface area. All right, so natural world knows this. All right, so I wanted to just say, I don't want you to read this. I'm just going to tell you a little bit about it. It's saying that there is a cluster size. It's not, I'm not suggesting that all small clusters will die immediately. You can handle them in insulated nuke boxes, but you can't expect them to be able to survive with added ventilation in an uninsulated box. If you had two colonies, one that is healthy going into the fall, and it's in a double deep, and it's, let's say, 7 seams of bees, and it's been cared for. And when I mean healthy, you know, it's low viral load, lots of work on its varroa through the season, and you come in, there's, you know, no other maladies in there, no other, you know, especially parasitic mite syndrome or any other kind of disease that it might have. If it's healthy going in, it can survive with lots of stores but in that case, if you don't insulate it, it might need some top ventilation, right? But if you took that same cluster in a large uninsulated box and you added top ventilation, it's likely dying. Now, smaller clusters in insulated boxes, they do well. And lots of folks overwinter nukes. I do it all the time. I overwinter singles also the same way in insulated boxes. I know there's folks here up in the Northeast in Vermont and even higher up in New York State that do well with singles that are insulated on and nukes that are put on skids and wrapped and insulated heavily, and they survive just well. So it's not just a matter of cluster size. There's management practices that can also help you get through that winter. All right, so I'm going to focus now a little bit on the hive gases and what occurs inside a cluster, and I want to make it clear that at this point we're going to be dealing with gases inside of a colony when we go forward and talk about the difference between ventilators and condensing colonies. And the gases I want to, when I say gases, I mean moisture laden. Humidity is one sort of gas. And then the other one is CO2, which comes from the natural respiration of bees. And those are the two sort of gases. Oxygen is in there also. But in a typical core, what's occurring is the temperature rises, of course, goes up in the core. So does the level of CO2. The oxygen level goes down and the humidity goes down, right? We talked about the bees in the core being a little bit dehydrated because this air can carry a lot of moisture and there's convection currents taking that moisture away and the bees are staying nice and dry. And then the bees on the outside mantle have a lot of metabolic moisture that they can't get rid of as easily because the temperature of the air outside there doesn't carry a lot of moisture, so it lays on their exoskeleton. Right now, the CO2 in this core can get high enough so that in severe conditions, when it's very cold, there'll be a big CO2 buildup, and you can read the numbers if you look up these numbers. I reference a study later on that shows you that you can get the numbers from this. Wow, the percentages of CO2, if you're interested in them. You might not be, but they're pretty well defined. But as that CO2 rises, which is gas that's generated from the metabolic action of bees heating the core, it can put bees into a hypoxia. Now, hypoxia would normally be deadly for human beings, but it isn't for bees. So for bees, what occurs is they go into an ultra low metabolic rate. So it's a biological adaptation that bees have to conserve energy, lower their metabolic rate when they're forced to tighten up their cluster and when the ambient temperature goes really low. All right, so I want to say again that bees are adapted to deal with the hive gases perfectly on their own. They know they fall into, by way of natural biology, they fall into these states that preserve energy and help them survive. That's part of the evolution that made warm-bodied bees be able to survive in temperate climates like ours. All right, so the moisture-laden air is finding its way up through this brood nest and out through the insulated shell, and it gives off a little bit of heat, and then it does its normal loop, convective loop, right? Heat air rises, falls down around cold surfaces, heat is attracted to cold, and if the top of this box here is above the dew point, the air will fall down. The moist air will not condense on that surface, will fall to the side and find its way harmlessly out with these blue arrows. I'll show you more about that as we go on. It's a little bit tricky to see it here. Right, but again, I explained how bees manage this piece in the core, how precise they adjust this convective flow. They do this precisely, and maybe almost like they breathe, or however they do it, whatever sense they have for the temperature of the core, however they figure that out, and whatever it is that sparks that biological response, they will meter the amount of air that flows through this center core precisely to control the temperature of the colony. All right, so we talked a little bit in that last slide about what a condensing colony is like. And here's the sort of basic contrast between the two. A ventilator vents out moisture, gases, and heat. And a condenser conserves metabolic moisture, gases, and heat, and also uses the gas to regulate the metabolic rate. So I talked a lot about that. My theory is, and my hypothesis is supported by a lot of other folks' work, and a lot of the latest work on thermodynamics of bee colonies by folks like Derek Mitchell and some of Tom Seeley's work, of really interesting folks that are involved in taking another look at what happens inside of a wintering colony. Think, along with me, that this piece where you're venting out the moisture, gases, and heat is something you can do and must if you don't insulate your colony and you have a lot of, and it's a big enough colony, has plenty of resources and is healthy and it's generating a lot of heat. So it works. I'm not suggesting that it doesn't work. And you have Dewey's wonderful article in the American Bee Journal where he outlined all the different techniques for wintering bees in a very measured and fair way. And he explains that really well. I suggest you read that article. And then a condenser, of course, is doing all the opposite. All right, and of course, you say to yourself, well, where did this idea of ventilation come from? Well, it wasn't long after we put bees in thin boxes with thin insulated boxes, we discovered that moisture will condense right under the or around the port of bee escape hole on a cool inner cover, and then liquid moisture will drip back down on the cluster and kill it, right? Because bees can tolerate cold way down to like -20 and -30. Folks have put bee colonies in freezers that went way down to -50. And as long as they didn't leave them in there for a week, they came out and survived. So cold is not what kills bees, but moisture and cold will. Right? So the observation by beekeepers over generations that they had to do something with that moisture, especially in an uninsulated box, and especially if the top is ventilated, especially if the top wasn't ventilated, they had to do something to ventilate that stuff out. All right, I'm going to skip this one and go right to the ventilation equipment. So here's some of the equipment that folks use to ventilate colonies, and I'm sure some of this might be familiar to use. There's quilt boxes here. I think that's a practice in your area, using quilt boxes and to capture moisture. And then this one, which I cringe at, but people still do, in the middle of the winter, they'll lift their inner cover and make sure that there's a real cold stream of air that comes up through the center of that cluster. Now, if you believe what I told you about the cluster's ability to be able to regulate its hive gases in natural circumstances, you might be able to recognize that something like this, where you're intentionally pouring a cold stream of air through that cluster, your bees are probably in a survival mode. Now, it's not that they can't survive under those conditions, but I mentioned earlier that that bee colony has to be very healthy, the right size, and have plenty of stores, and it'll work. You can get it through. And these are quilt boxes. There's more on quilt boxes. This is my favorite one, a solar ventilator. This is a contraption where somebody has a little computer fan and a little solar outfit that actually pulls cold air through that cover. Yeah, I mean, that's an interesting one. Here's some quilt boxes. I think you guys know what these are all about. I don't think that, I think that they collect moisture well. They add some ventilation, and they also, but in my opinion, I'm going to argue that they capture the moisture that bees need in the box during the winter, and I'm going to get into that next. All right, so if you look back, and if you've got some time to read a little book written by a beekeeper named Ed Clark back in 1918, you can read a lot about what he calls constructive beekeeping. This is a little quote from Ed, and he when I first read this, I don't know how many years ago it was now, I got to start to think about, what is he called them condensers. I call it a condensing colony. And he thought that bees were trying to tell us something. If we observed the way they prepared our box for winter, what they do with the propolis and all of that, he was suggesting that we're going to follow their lead because they're telling us something about what they want to do when it comes to controlling the gases inside their colony. And especially as bees prepare for winter, I think you all will agree that they want to propolize the boxes shut. Now that's, they do it in the summertime also, but And the summertime, the same, I think it's done for the same reasons. Propolis is used, one, to keep predators out of the colony, and two, to make certain that they can control the hive gases in exactly the way they want to do it. And Ed was optimistic that we would be following where the bee leads us. And I'm not sure we have yet, but I think we're getting there. There's more awareness of looking at the way bees control the moisture and condensation in their hives naturally. Right, so I just have a couple of little illustrations of what propolis, a really strong colony that's wanting to do something with propolis, does. Here's a wonderful line of propolis that was sealing 2 boxes together, and that's, when you pull it apart, it came up in those hairs. It's great to see this. I love it when this happens. This is actually a nuke box, and this is the feeder I had on that nuke box. I flipped it upside down. It's a beautiful line of propolis all the way around, and it was just sealed shut beautifully till I wrecked it by taking it apart. And so are bees trying to tell us something? I think so. I mean, you look here, you can see how this particular bee escape hole, this was the fall. I pulled this off when I was putting on my insulation sleeves, and the bees had already sealed the porta bee escape hole completely shut. And it's flat like that because it was touching the inner surface of the telescoping cover. And again, I fabricated some entrances that had a wonderful crown shape to them rather than just a square opening. I saw the idea in Europe, and I thought it was a great kind of entrance, and I made a few, and I put them on colonies, and they put this sort of lip down the center and divided the entrance into 2 entrances because it was too wide over here. I think these bees made a lot of propolis, and this was on for a while, so they had a chance to modify that space as they see fit. All right, so in a natural colony, I want to talk a little bit about what occurs inside of a tree. And this is a little diagram that Celie wrote up, allowed me to use. And if you look at what occurs inside of a tree colony, you would note right away that there's wood above the colony and almost an infinite amount of insulation. That wood can go up 10 feet, 14 feet. And although wood's not a really incredible insulator, enough of it would provide plenty of R value above the colony. So this surface, as heat rises off the cluster, this surface in a natural colony stays warm. And what this is illustrating, this thick black line, is a propolis shield that bees will make around a natural cavity. And I've witnessed this a number of times in my own practices where I've been asked to come out and where bee trees have been felled either by accident or by storm. And I was then extracted the colonies and noticed the, well, actually I took them home, took the section of the colony home and chainsawed it in half, and I could see this beautiful propolis cavern that's built inside of bee colonies. So it's waterproof, kind of water resistant shield. And so that all of this wonderful heat that's generated is captured on the top and stays nice and warm. Now, on the bottom, the same thing. You'll have just as much insulation on the bottom as the top. A lot of times trees are, 10 feet. Bee colonies are 10 feet above the ground or 5 feet above the ground. Some that are on the ground also, but either way, they have a lot of insulation on the bottom and the top, not so much around the sides where it's cooler. And that's works in perfectly with the condensing colony concept, because if these walls are cooler here, that means that all the hot, moist air that hits this warm surface and then tries to find its way toward a cooler surface will fall harmlessly outside the bounds of the cluster. Right? This is just another example of it. This is just what I explained to you. Warm surface above the tree colony and cooler surfaces on the side where they act as condensers, where the vapor forms. All right, now here's an illustration of a cover that is an insulated cover, and I'm going to show you a little bit more about how this one is constructed. That's allowing this colony to act as a condensing colony. So you'll note that it's sort of subtle, but you can see it, that this surface right here is what the cluster is heating. Now, this is the middle of the winter. This is like January. And I pull it off to see if bees needed to feed or something like that. And I snap this little photograph. But here's how the colony runs all winter long. This is clear as a bell. No moisture occurs over the top of the cluster. No top ventilation at all. Totally sealed. The only entrance is down below. Little 3-inch entrance down in the bottom. And you can see that as this hot moist air finds its way across the surface, seeking out cooler spaces, it discovers them right on the edge of the box up top. And this, of course, is where liquid moisture forms. Now that does a few things. I'll explain in a minute what that does for bees. All right, so I wanted to make sure I did a sort of fair analysis of the difference between, say, a ventilator and a condensing colony, and I would say that some of the minuses, this is my opinion about what the minuses are for a ventilator colony. As I mentioned, I think it vents out heat and gases and moisture that the colony wants to actually conserve based on their natural tendency to be able to control the hive gases on their own. They require a large reserve of winter honey. Sometimes that's hard to get. A lot of times you have to feed like crazy in the fall to get that. And I think they can put, and most likely do, put a cluster into constant survival mode. Now, it doesn't mean that they're going to die that way, but that means that they have to generate a lot of heat. Hence the need for lots of stores for them to be able to do that. Small clusters, of course, die faster. And heater bees, as I mentioned earlier, there's some controversy about heater bees, but they're likely to suffer in some form from oxidative stress. The pluses are it'll keep the colony dry, and it may help. I don't have much data to support the fact that it will kill pests, but I think there's some obvious advantages, especially if you have small hive beetle load going into fall. A cooler colony might not be good for them. Wax mort, of course, are gone by the time you get around to winter. There's lots of available equipment. There's lots of history. There's lots of folks that'll tell you exactly how to do it. And it works well with large, healthy, well-provisioned colonies. I can't stress that enough. You know, no colony that goes into winter with a dearth of winter bees or winter bees that have been the subject of varroa predation, those colonies won't live under any circumstance. They usually die at the end of December. And in my area, they die at the end of December. All right, so has to be healthy. Condensing colonies, they require modification of equipment. That's a minus. And that equipment includes significant insulation, especially on top. It's not an intuitive way for beekeepers to keep bees, and it's contrary to the common understanding of colony management. So those are some of the things that I think make some sense. I think it's a natural way to keep bees. I know it requires less honey for overwintering. I always have colonies in my yard that are side by side. Some of them are insulated in condensing colonies. All my production colonies, I try to get into winter really healthy, and I try to get them in my insulated sleeves by now. I've only got a couple left to do. And I always winter my nukes side by side in doubles, and or a large insulation sleeve over a 5/5 nuke configuration. And they require less honey for overwintering. I know it for a fact. I want to say that after about 7 years of keeping bees this way, a change in my practices of providing ventilation and other sources of another method of winter survival, this has reduced my winter losses. In my case, for me. All right, I want to go back and encourage you to try to get through some of Derek Mitchell's work he's done some really good stuff. He'll give you a headache with his formulas, but he does have some plain language in a lot of his scientific work. This one is interesting because it talks about the difference between the thermal conductance of a tree and nests and natural colonies, and it makes some really interesting points. One of them being that there's 5 to 7 times the heat loss in a thin uninsulated box, versus you can see the tree cavity here, bunch of wood around it. And this one was in the middle of a tree. This was probably 10 feet off the ground, and the tree went up for another 35 feet. So, there's a lot of insulation above and below. So trees don't have, thin uninsulated Langstroth boxes don't have a chance against the insulation quality of a tree. So lots of times folks want to know what is insulation and and I want to stress on this view, what isn't insulation? All right, so I think the best insulation that we can come up with for insulating colonies is a foil-faced foam board. They call it B-Max. You can find it in the big box stores. It has foam on. It has a closed cell foam, which is referred to as polyisocyanurate. It has the highest R value, and it has foil on both sides. And with foil, you have an opportunity, as I mentioned earlier in the talk, you have an opportunity to reflect back a little bit of IR, infrared radiation, back to the bees. Right? There's no study that shows how much or if it's even significant, but I know it occurs. And it worked in thermal envelopes that I built for or designed for industry. So I'm sure it works for bees, which is nobody has ever done any science about the IR loss on bees and how you can reflect it back to them. Then there's the XPS foam. I use that a lot for nuke boxes, but I also cover that with a foil surface for anything that faces the bees. That's for 2 reasons. The foil keeps the bees from chewing out the foam. They get a little antsy during the winter when they don't have anything to do. They'll chew that foam a little bit away, and you don't really want that. It just makes a whole mess of dust inside the colony. Doesn't hurt them, but it's just not pleasant. So if you put that a foil face on your XPS foam, if you use it, it'll keep bees from chewing it, and it'll give them the same sort of IR reflection that you're trying to achieve with the foil face polyisocyanurate. It's better. The worst thing I think you can possibly do inside your colony is put Homosote. I'm not sure if that's a practice where you guys are. I know that they still sell this stuff at the bee houses for moisture boards. The thing about Homosote, it was designed for use inside of building bays and dry building bays, basically for soundproofing, but did have a little R value under 1. Of course, it immediately goes away as soon as it gets moist. It has no R value after that at all. And it does hold moisture. It will get soaked. Sometimes you'll hear folks that want to use Homosote talk about, hey, I had to change it. It turned into an ice sheet. And it will do that. And under those circumstances, it's not really doing much for the bees if you have an ice cube above them. And also, they can't get at the moisture. And if they do try to get at the moisture in Homosote, they discover that it's loaded with borax. So Homosote has a insecticide built into it because, as I mentioned, it was designed to be used inside building structures, and they thought the best thing you could do is put an insecticide in there while you're putting in a sound barrier. That way, if insects get in there, they die. And I don't have any statistics about bee loss from Homosote, but I'm sure it doesn't make sense to me to put it in there if you don't need to. There's plenty of other insulation materials you can use. All right. The other thing that's not insulation is black roofing paper, known as tar paper. It has no R value, so it's a good windbreak, but it has no, it's just not insulation. And I hear folks say, well, it heats the colony if you put it on in the wintertime. But I'm not sure if that's actually true. I don't know. Bees will find their way as the sun moves around in the sky. If you look at some of the IR photos that have been taken recently by folks like Etienne Tardif up in the Yukon, and other folks that have done some really interesting IR work about how their bees move around in a winter cluster, you'll find that they do actually move over to the side of the box where there's some sun in the wintertime, assuming that there's a strong enough sun for bees for it to make a difference to bees. I don't know if they're following a heat signature or they do that for some other reason, gravitational pull, who knows? I mean, we know so little about the biology of bees that we can't really tell much about their behavior from stuff like that. But I know that, if you've got a couple of good honey frames between your bees cluster and the outside wall, those honey frames will not change temperature with a piece of tar paper on them, even if the sun's blazing down on them. And anyway, surface temperature and thermal mass are two different things. You need thermal mass to raise the temperature of the wood and the honey frames next to it. All right, Homosoap, we talked about. Bees Cozy products, I'm not sure about them, but I'm sure, I know some of them do add some protection from wind infiltration. All right, so again, most of the heat loss in a Langstroth box goes out of the top. You can see that with those illustrations from how the convection flows. The warmest part of the colony is up on top, gives you a little heat crown in the top that provides some pressure, downward pressure, which keeps a lot of drafts coming inside the colony. If you don't have them ventilated, of course, I'm talking about a condensing colony. Right, so most of the heat goes through the top, and then folks have come up with ingenious ways to make insulated tops. But what I've noticed, and I noticed this more and more, there are companies all over the world that are making insulated boxes, foam boxes to do the work for us. They've already made what you would consider condensing colonies. And there's lots of manufacturers out there that are building these ready-made boxes that you can actually just put together and they'll already act as a condensing colony. Some of these EPS boxes, these are not XPS, these are EPS. Some of these different compounds require some control of the bees from chewing it. So you'd have to be very careful about that. But there's plenty of choices. If you wanted to try one of these, you could just buy one and try it and see how a condensing colony works in your own yard. I, of course, have done this because when I started this, there was no alternative. Even the Bmax box wasn't even out yet, which is I think the first sort of version of a foam box in the US. So I built these sleeves. And here's the way my sleeve construction works. This is what I would consider the basics of a condensing colony. It's a sleeve that goes over the box, polyiso sleeve, Bmax or whatever you want to call it. Has foam foil on both sides. Then I put a feeding shim in it. You can notice that there's a space between the top of the box and the top of the sleeve. I put a shim in it, and after the shim's in, it looks like this. There's still a little space here, so that when I put the telescoping cover on, if you looked inside, you'd see just this, right? The insulation touches. The sidewall insulation and the top insulation inside the inner cover touch to make a complete insulated shell. And that's actually as simple as it gets. It's all you really need. And at that point, if you wanted to run a condensing colony and try one, that's the extent of the work you'd have to do. And if you made this, by the way, out of 3/4 inch, then you can buy a standard top, Bmax top, and you wouldn't have to make a special telescoping cover like I did here. Because when you put a sleeve around a box, it increases the outside dimension. So a regular telescoping cover won't fit over it anymore. And you really want to make sure that these two insulation surfaces meet, this one and the top insulation. And as you can see from that photograph I showed you before, the bees will heat this. Actually, what occurs for most people that run these, this sort of style of condensing colony has had some, what I would consider conservative acceptance all over. Folks have built them up and down the East Coast. I've gotten reports back. Folks that have built this design, tried it, and had lots of success. I haven't heard about any catastrophic failures yet. Of course, bees will die in these, and there's nothing that'll keep a sick colony alive or one that's just not going to thrive. But it doesn't, I haven't had any negative effects on it. Bees will die. You will find, if you find a dead colony come springtime, there could be a lot of mold in it, but that's not from this configuration or lack of ventilation. It's because the bees died. The bees were wet. They gave off, each one of them gave off, 50 milligrams of water. And if there's thousands of bees, all that moisture was inside that box, and it, can create mold. So I don't hear about mold problems. I know that they've been built for as far south as Georgia, and been used with some success. And there's some out in the West Coast out there with you guys. What we don't have is a body of science that supports the we don't have a body of science that supports a trial that would look at the different, some really controlled peer-reviewed study that shows the difference between how a condensing colony works and a ventilated colony in a field trial where you had, I don't know, 25 or 50 ventilated colonies, 25 or 50 condensing colonies, and then some control colonies, which you didn't do either two, and then did an actual study. We don't have that science yet. We need that because it would lend some credibility to what I think is a sort of growing anecdotal accumulation of knowledge. So anyway, that's all I have. So if there are any questions, let me know.
Oh, we have lots of questions. So I'm going
Okay.
to start with the earliest one, which is from Joan. And she asks, how important is it to insulate the bottom?
Not at all, actually. So I'll show you why. And that's a great question. And actually, these are things that clarify the talk. The reason for that is right on one of these. All right, so if you look at this photograph, as I mentioned to you, this IR photograph I took was in January, and you're looking at, I have to pull the sleeve off and the telescoping cover to take this photograph, because you can't take a IR photograph through a foil sleeve because it just bounces back your own image. So if you look at it, the temperature down here below the cluster is about ambient temperature. So the heat dome is up here. That's where the insulation, and in this case would be the most effective insulation would be from wherever there's heat. Down here, you don't have to insulate the bottom. But what I do down there is I put in, if I have a screen bottom board, I will put in a Luan block of, regular piece of solid wood under there that will stop the upper currents, any air current from blasting into the bottom of the colony, but that's not likely to occur because, as I mentioned, there's a heat dome over here that puts a little downward pressure on the entrance, so that there's not a lot of natural airflow that comes in the bottom.
Great. And I think, Eric, that hopefully answered your question, because you also asked about what from the bottom, of an open screen bottom board for heat loss in comparison to top and side. So if that didn't answer your question, you can type it in or just tap on your space bar and ask. So John asked, what is the name of some easily commercially available insulation?
All of that stuff, that RMAT, those foam boards are all commercially available.
Great.
Right at the
And-
home, right at your home center. You can buy them in 2-foot widths. You can buy them. As a matter of fact, I couldn't believe this. I was so fortunate. We had a bulk cleanup this year in my neighborhood. I mean, this is incredible. I mean, somebody threw out 2-inch XPS foam boards, 2 feet wide by 8 feet long, about 5 or 6 of them. I picked them up and washed them off with my hose and made bee boxes out of them.
Joan also asks, should the top vent hole be plugged?
Well, yeah, the whole point of this, if you want to try to run a condensing colony with an insulation barrier all around the box, yeah, then yes, that's exactly, yeah. The top, there's no top ventilation in that scenario.
Okay, and then based on your viewpoint, ventilating the hive, no, condensing hive, yes, but we don't have really severe overwintering conditions in Oregon for our bees. Could you talk to that?
Actually, I'm not sure if I want to make certain that you understand this, right? That a colony that's in the condensing form, in my opinion, does well biologically no matter where it's located. As a matter of fact, I'd be so bold as to say I think you could leave the insulation on all year long. I definitely leave the top insulation on all year long. But if you have an overwintering strategy that works for you, and you don't see any downside to it, then you, by all means, that's what you continue to do. What I'm presenting here is what I think is a different management configuration that's more in line with the way bees naturally live.
And so this may be a little redundant, but Jess wants to know if you compared a fully enclosed hive with a hive equipped only with top insulation, because again, in our milder climate, she wonders if that might be sufficient.
What sufficient?
Just
what might be-
you want me to read it again?
Oh, the combination of insulation and ventilation, like the two
Well,
together?
Have you compared a fully enclosed hive with
Yes.
a hive that's only had the top insulated?
Oh, only with the top insulated. Oh, yeah.
Right.
Yes. Yes. In milder climates, yeah, the sidewall insulation is not as important. But what it won't, and it will, you will get some, what you'll get is the same sort of pattern on the top. So that what will occur on the inside of the inner cover, what will occur is that same sort of clear spot over the top of the cluster. But you'll get a different moisture distribution pattern because you'll end up with a cold comb right away. So I try to control that piece by insulating the outside boxes. But yes, you can get, it might be just sufficient for you to put insulation over the top without ventilation.
Okay. And then I think on one of your final slides, it didn't look like your telescoping cover had any insulation. So Patty asks, did you insulate your cover?
Where was that?
I think it was the very last slide. I mean, I kind of noticed too, you were showing us the insulation on the what you had built, but
Okay.
and maybe it's
Yeah.
we
Yeah,
don't
and
really
this-
get to see the
Yeah, so this cover, right?
right.
If you turn it up, if you put it on top of this box right here, this one, right? And you
right?
flip it up like I did here, that's what it looks like.
Ah, so what we're looking at is we're looking at the
The
insulated inner
underside of the
cover.
telescoping
Right.
cover.
That wasn't
Sorry.
perfectly clear.
Thank you. Thank you. Thank you for that.
Okay.
Hmm.
So somebody says they have a peaked roof build that sits on top, and he was stuffing it with wool batting. He asked if he should keep the vent hole open on the top.
Above the insulation?
Corey,
below the-
can you just press on your space bar, unmute yourself, and just clarify your question, please?
Yes, above the insulation on the peaked roof.
Yeah, I mean, that's just like your attic would be configured.
Yeah,
I mean, it doesn't, that insulation, that, you don't have to do that in a beehive, but that makes sense if you have a moisture problem in your house. But you're gonna put in a bunch of insulation that is what, down on top of the bees? You have that beautiful, what do they call them, garden roof, right? Which has a gable.
Mhm. Yes,
And is it a top bar hive or a regular hive?
top, yeah,
Top bar hive?
yeah.
And you put the insulation right down on top of the top bars.
Oh, I've got a box with a spacer that goes on top of the top deep.
Oh, okay. You're talking about a regular Langstroth colony. Yeah, you have a spacer. Yeah, I mean, just as long as you don't put ventilation below insulation, I see that a lot. That is like, you might as well just take the insulation off because, you know, it totally negates any kind of R value, any kind of ventilation over the under insulation.
Okay.
Well, I don't see any more questions. Does anybody have any further questions? If you do, you can simply press on your space bar and shout them out. Ask them. This is your chance.
I have a question that kind of talks what you're talking about for keeping insulation on during the summer. So I
Yeah.
insulated my hives this year during the winter, so just a few months ago or a month ago, and I've seen a significant increase in the temperature and a drop in the humidity. My logically thinking if I keep that insulation on during the summer, would that also help to reduce the stress the bees experience with the heat exchange and may lead to better hygienic practices or something else, whatever they would then devote their energy to, which they otherwise would be fighting off pests or other things like that?
Wow, that's a wonderful question and a great observation too. I'm assuming you have some kind of a brood minder or something in that colony?
Yeah, it's just a homemade one that just measures temperature and humidity, but yeah.
Okay, so you have some kind of little device. in
Yeah.
there. Yes, I mean, I think the answer to your question is absolutely yes. If a colony is not, by the way, if a colony with top ventilation during the winter is preoccupied with survival, they cannot be attentive to the other duties that can occur inside of a winter colony in preparation for brood rearing in the spring. All right, so the same thing occurs in the summer, in my opinion, that if you keep your colony in a more natural state, they use one thing we didn't talk about, and I was explaining this to Dewey earlier, these sort of extemporaneous talks, you always miss something. And what I missed to discuss in this one is that when bees are, when moisture condenses inside the colony surfaces, it's available to the bees and they can use it to thin honey. They can use it to cool cell. In the summertime, they can use it they use water in the summertime for everything inside of a colony to cool it, to thin honey, to do all kinds of things, right? They have that. If you're always drying them out in some way, or in your case, maybe introducing a big humid airstream inside the colony with ventilation and all that, then yeah, they're distracted from all the rest of the duties they have to do. They have to survive no matter what, and they're going to take their heat, by the way, and cooling is a big occupation that bees have to do to survive. So it's you can distract them, and there's literature on that. You can read about that, but that's why I keep the top insulation on all year.
Do you have experience with hives before you started insulating them? And I
Oh,
get,
yeah.
I'm not super concerned with over winter loss. But I didn't know if you had seen a difference when you started insulating versus when you didn't.
Yes, I have plenty of experience with uninsulated colonies, and I have I think I have about 8 years experience with condensing colonies, and yeah, I see a difference. But the other with survival, but the other interesting thought you might want to keep in mind is if we're in an era now where it's not like when the mythology and bee lore about ventilation began, right? We don't have the same bee. The bee we have is a bee that has lots of stresses, environmental stresses, loss of habitat, lots of pesticides in the colony, and then the predation of varroa mite, feeding off the fat bodies in bees. I mean, think about what our current bee stock is up against to try to survive. My thought goes naturally to, why not give them an environment where they're more accustomed to living in, and they've evolved in over millennia, and that they're biologically adapted to control all of those other gases. Maybe something good will happen, and they'll have a better way to, a stronger immune system, or they could spend more time on propolising the colony. Who knows? But yeah, I have experience. I think that I can say with certainty that I think my bees, are healthier in condensing colonies, and that's a belief. So as I mentioned, we need some science for that.
So I have another question here, and this is actually something I've noticed about my own bees, is Dion has one colony who just insists on using the top entrance, even when she moves the queen down. Up to this point, she has let them use it, even though she does keep a small entrance at the bottom too. And she asked, do you think she should close it and force them down for the winter time?
Well, that's always been a problem with upper entrances. Bees learn, and they have a long memory, by the way, about that also. And they also have a footprint, a trail to that upper entrance. You can learn that if you ever you will learn how subject bees are to follow an entrance patterns into the colony. If you ever use a robber screen, and then you get past the robber screen need and you take it off, you'll notice that your bees will land on the face of the colony exactly where they were landing, where they made entrance through the robber screen, the colonies that belong there, the bees that belong to that colony. Even with the robber screen off, they still walk down the face of the colony and go in the entrance the same way they did when the screen was on there. And they won't stop doing that until that generation of foragers leaves. Same thing with upper entrances. They will stay at that upper entrance. They've learned it, they'll stay with it. Moving the queen down has nothing to do with that. Their use of the upper entrance. And if you, in a situation when I used to ventilate hives or have an upper entrance for the summer in my colonies, I would always have to try to train them then in the winter to stop using that entrance, and that takes weeks. They fly around it for a while, and then they find their way somewhere. I don't know if you lose them. I always felt uncomfortable, but if you block it, they'll stop using it. after a while, but
Okay, does anybody have any final questions?
Yeah, I do.
Okay, Bruce?
Do you insulate the supers when you put supers on?
well, I don't have supers on in the wintertime. Are you
No, I mean,
talking about honey
You
supers?
said you said that you advised that it would be advisable to insulate in the summer. I was thinking if you do it in the summer, do you insulate the super?
Well, I don't run, I said you can leave the insulation on all summer long. Now, I know that there are people who not, as a matter of fact, I'm trialing an insulation sleeve that that I think I can divide and put around each box. The problem with having a full insulation sleeve over 2 deeps during the summer is that you can't work the bees, and you always have to have access to the bottom box for something now and then, especially if you might even want to use a treatment piece, some kind of treatment chemical on the broods down in the bottom box. You need to get to it. So it's hard to actually do your beekeeping with the sleeve on all year long. But if you could, then of course your supers would be over the height of that double sleeve. And then you would have to, if you wanted to try that, which I encourage, you'd have to build another small sleeve that would be the height of your super, put that on top, then put the insulating cover on the top of that. Now, yeah, you could do it that way.
Thank you.
One more question.
Yeah.
So do you have a recommendation for an IR gun to measure the temperature? Make model is exactly the make model that you use or recommend?
Well, so I use a little flare. So I have a flare camera that I bought for an iPhone 5. And I use that. It's an interesting little adaptation, a device that you slip your iPhone in. The problem is that it only works with iPhone 5, and I'm stuck with it, and I have to keep my iPhone 5 alive to actually use my IR camera. And you know what it is, where we are with that now. So what I recommend you do is get one of those little cost-effective dongles that go in the bottom of the lightning port or charging port of the kind of phone you have. If you have an iPhone, it has that. They hang right off the bottom, and they'll move with you from phone. I don't think iPhone's going to change the lightning port anytime soon. It's proven at this point they're going to keep it. Now, I don't know if you have another kind of phone like an Android or something. I'm not sure what that configuration, that charge port configuration is like, but they also sell these little dongles. They hang off the bottom of the phone, and they do a wonderful job because you don't need a big sophisticated IR camera.
Yeah, so we have iPhones, so that's great. But where would you find such a device, and exactly what is the name of that device?
Oh, I use the flare cameras.
No, I'm talking about the dongle.
Oh, I don't. So I don't know. I've seen them. I don't have an exact. I mean,
I bought
an
the
internet
same
search. Does somebody have one?
Yeah, I bought the same FLIR, and I have an Android, and I bought that dongle off of the FLIR website. And around Christmas time, FLIR will tend to run specials. You can't really get them on special from Amazon or any other retailer, but
Okay.
directly on the FLIR website, they have a lot of all those little things that make it work. The dongle.
A little dongle, yeah.
Okay.
And so go to the FLIR website. I mean, and it's so much fun to have even the sort of basic, I'm gonna show you mine. I mean, it's just plain fun. Here's what mine looks like. So there's the iPhone camera, right? It's on the bottom of it's an attachment to an old iPhone 5 of mine. So you take the iPhone out, and this is the camera. And here's the iPhone. And, it drains the battery in 10 minutes, but it's a lot of fun. It's so much fun to have one.
And you can also do things like I bought it for my husband because he was doing a lot of duct work under the house until I pretended like it was for him. And boy, he just went down and took pictures of himself, the cat, all the duct work. And it was really handy to see where the leakage was with his ducting.
Yep, I use that little one you just saw for bee removals. I find where they are in the wall. You know, you can find the exact location of the colony. And even though that wasn't really expensive, I think it was a couple $100. It does a great job.
Well, Bill, thank you so much for coming to the West Coast and talking to the Portland Urban Beekeepers. And if you're ever in town, stop by.
I will, yeah. So thanks for having me. I appreciate it. It's midnight here on the East Coast.
Oh my
so-
goodness.
So I'm about to hit the hay at this point, but it was a pleasure to talk to you folks. And thanks for inviting me, and I hope you came away with some ideas about how condensing colonies will work, and how natural colonies work inside trees, and so on and so forth. And there's plenty of literature to read. You recorded this section?
Oh, we did.
Yeah, so you can have, you have plenty of material to look up if you want more information.
Perfect.
Thanks
Thank
so
you.
much.
Thank you. Good night.
All right, bye.